Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in a branch of chemistry, of course, that we refer to as stereochemistry. And this is a branch of chemistry that deals with the three-dimensional aspects of molecules. So in this case, we have been doing some of our demonstrations using a linear representation of molecules. But in actual sense, these molecules assume a three-dimensional structure, or rather structures that we're going to look at into later. In this case, of course, the concept of stereochemistry stems from the fact that we have to have a different way in which we are going to place these atoms in specific molecules. And this dictates the chemical reactions of these specific compounds, which are formed by these three-dimensional structures that we're talking about. So under the concept of stereochemistry, we're going to look at the concept of enantiomers and, of course, what we refer to as chirality. So these specific characteristics are going to lay for us a basis in conformational studies. So in this case, I thank you and welcome. So as I've said, today we're going to look at a branch in chemistry, basically a concept in a branch in chemistry, and this branch is stereochemistry. And this basically, as I've said, deals with the three-dimensional arrangement of atoms and molecules. And this, of course, has an effect in their chemical properties of these specific molecules. So this deals with the three-dimensional arrangement of atoms and the molecules in structure. So in this case, of course, we are going to look at how we can be able to represent specific atoms and molecules in structure. And this is going to, of course, have an effect on their chemical reactions. These specific arrangements are going to have an effect on the chemical reactions of the resulting molecules. So as I've said, under the stereochemistry, we're going to look at the concept of enantiomers and the chirality. So these two specific concepts are going to give us a basis on studying other concepts which are going to proceed from this, which deals with, of course, the concept of conformation and the arrangements of this specific kind of molecules. So in this case, we're going to have a breakdown of this particular concept by having a demonstration of a few molecules which we're going to use in our discussion, which are going to give us the concept of what we refer to as enantiomers and the condition of chirality. So in this case, we're going to look at a demonstration of molecules which are going to give us a concept for this. So in this case, I just give a demonstration and then we have to have a look at that. Now in this case, I've done three representations of specific molecules. And don't worry about the details, I'm just going to explain from step number A, B, and then we'll just finish with C. So in this case, I've drawn different setups of arrangements, three-dimensional arrangements of molecules. And we're going to see whether these, of course, molecules are going to obey the concept that we're going to talk about, which is going to give us the concept that we have discussed about the enantiomer and chirality. So in this case, we are going to have this one as our mirror line. So this is the mirror. And this is the mirror. So the dotted line that I've drawn in between is what we're going to have. So comparatively, we're going to look at how these different molecules can be illustrated. So let's start with the first one here at case number A. So in this case, suppose I have a molecule that has got a spatial arrangement of this kind, whereby this is the carbon, hydrogen atoms which are attached. Of course, at one point there's a substitution of an atom which is X. So therefore, we can give a general representation of this particular molecule as CH123, and then there's an X. So this is a formula for this specific molecule. So in this case, if you do a spatial arrangement for this, basically this one will be a tetrahedral molecule in shape. So this is a tetrahedral molecule. So therefore, we're going to see that this specific kind of a molecule has got a single substitution at this particular point for a molecule of X. So if we try to do a mirror at that particular center, we can be able to have an image of this specific molecule. Let's say that this is molecule M, and then the mirror image for this is M1. So in this case, if we do a mirror image, we will find that the mirror image is going to be just be the same as the parent molecule which is there. So therefore we can conclude that M is equals M1. So therefore our conclusion will be that the mirror image of this particular molecule which is M1 is the same as this one. So this is a chemical compound, and therefore this M1 will consist or contain the same chemical properties as M1, and therefore that one will be a mirror image. So we can therefore say that this mirror image or this compound can be able to be superimposed on its mirror image. So these are the same compounds. So suppose we have scenario 2 whereby there's a substitution at point, this one there was a substitution at this point X, and there's a substitution for hydrogen at this point Y, of course. And if we try to do the same step for this kind of a molecule by finding its mirror line, we'll find that the image that is going to be formed, M1, I mean this is M1, is also going to assume that M is equals M1, whereby for these two dye substitutions, there will be a mirror image that will be formed, which will be of the same compound as the first one. Now for the third scenario, for this second one, we have this is CH2 X Y. So therefore, a molecule of this nature, which is a tetrahedral, can have a mirror image, which is demonstrated by M1. So therefore, the two are the same compounds. So this, for the first case, these are the same compounds. The compound and its mirror image are the same compounds. So number 2, henceforth, these are the same compounds. So the difference between these two, as we are seeing, is a single and dye substitution at this specific point. Suppose we have a molecule which has got, of course, 3 substitutions, that is at point X, just like the first one, and then point Y, just like the second, and then there is an additional substitution at point, which is going to be point Z. Let's have this one as Z. So therefore, there is a substitution at X, Y, Z. So for this molecule, which is the, oh sorry for this, this just is the second one. This is a substitution at point Z. So there is X, Y, Z. If we try to do a mirror image for this particular compound, so this is M1 and M, and this is M1, where M1 is its mirror image. If we try to do a superimposition of this kind of a molecule, we'll find that we will have a different kind of a molecule, which is going, of course, to have M1, M and M1 not being the same compound. So therefore, M1 is not the is not a superimposition of this molecule, which is M. Therefore, we will conclude that the compound which is formed by this particular set of a molecule, which is a C, is 1H, X, Y, Z. This is the general formula for that kind of a molecule, and therefore we can conclude that that category or demonstration for that kind of a molecule is not superimposable on its mirror image. Hence, the two are not identical. So if we compare the 3 scenarios for A, B, and C, we'll see that a molecule that assumes this can be able to be superimposed. For a tetrahedral molecule of this nature, it can be superimposed on its mirror image. The same case for the second one, whereas we have a contradiction for the third one, where it's not going to represent a mirror image of that specific molecule. So therefore, we have said there are 2 different compounds for C, and these 2 different compounds, where the mirror image is not the same as that of a compound, are called enantiomers. So if we try to develop this idea from this particular case for scenario A, B, and C, the difference that occurs in the scenarios C is what leads us to the concept of what we call enantiomers. So therefore, we can conclude that for enantiomers, these are compounds that cannot be able to be superimposed. It's a compound that cannot be able to be superimposed on its mirror image. Therefore, these compounds are referred to as enantiomers. So we're going to look for a general representation of this concept of enantiomers and what they specifically are, and that's going to lead us to the concept of chirality. So let's have a second demonstration for that. Therefore, from our demonstration and illustration C that we have already looked at, we can conclude that enantiomers result whenever a tetrahedral carbon bonded to four is bonded to four different substituents. So in this case, of course, we have looked at that structure that was represented by these, whereby the first, second, third, and fourth kind of bonding that is bonded to the structure. Of course, we can be able to represent this one in different ways, maybe X, Y, Z, W, etc. So in this case, if we have enantiomers that result, of course, a chemical or a formula or a molecule that result from the bonding of four different substituents on the carbon atom, then we're going to have a compound that we call an enantiomer, or a molecule that we refer to as an enantiomer. So I've said we can just have a different illustration for that. So you suppose there is a different substance at those particular points, and we can be able to call this one an enantiomer. So this is a general representation for such a kind of molecules. For example, we can be able to give just a specific one for an enantiomer. Just pull this structure on the other side so that we can be able to use it. So this is Y, Z, W, and this is X. Four different substitution of the carbon atom result in the compound that we call an enantiomer. For instance, if I have a compound like this, whereby we have substituents as OH, H, and then there's another one which is a methyl group, and then lastly we have a carboxylic group at that specific point. So we have four different substitutions whereby we can see that the substitution number one, if we try to name it in just an arbitrary way, 1, 2, 3, 4. So for 1, 2, 3, 4, those are four different types of molecules or just atoms. For the case of hydrogen, which have made this carbon to have a substitution of four different, therefore making it a molecule that we have referred to as an enantiomer. So in this case, we're going also to look at just a different structure for this. For the sake of a demonstration, we can just have another one, which is a carbon atom with four different substitutions at these specific points, where we have an amine group and then a carboxylic acid group, and then we have, and then an alkyl. This is CH2, H3C. So in this case, this is a different kind of a molecule that we can as well refer to as an enantiomer, which is having this carbon and four different substituents in its structures. So therefore, for structures that are chiral, if the structures can be regarded as chiral, so we're just moving to that concept. So structures can be regarded as chiral if they cannot be superimposed upon their mirror images. So these are structures that cannot be superimposed upon their mirror images. So in our introduction to organic compounds, we talked about the branched chains, chiral molecules, etc., which can be regarded as organic. So in this case, when we're trying to talk about chiral compounds, these are structures that cannot be superimposed upon their mirror images. So therefore, the concept of chirality comes from there, in a way that, of course, this deals with a geometrical property of molecules or ions. In this case, I've just used two specific, so I'm going just to define it so that we can be able to see why I've used this term ion. So I can just be able to write that, and I have a small demonstration for that. So if we have a tetrahedral molecule of that nature, then we can be able to refer this one to as an enantiomer, because it cannot be superimposed upon its mirror image. So suppose we have this is a molecule. Suppose we have an ion. Of course, this ion is going to be tetrahedral, just like this molecule. So this is a tetrahedral. I'm specifically going to use the ammonium ion simply because it's the one that we can generally relate to, which has got a tetrahedral structure, but not basically assuming the concept of an enantiomer. So I'm going to use that one for demonstration purposes to show how ions of that nature can be able to form an enantiomer. So given the fact that it is forming that kind of a structure. So if I have ammonia, which is a molecule, it's going to have its structure as that. So remember, nitrogen on that one has got those two lone pairs of electrons. So therefore, suppose we form an ammonium ion, in this case, then we shall have nitrogen forming a hydrogen at this specific point, and this generally is going to give us a ammonium ion. So that case, this kind of an ion is a tetrahedral kind of an ion, which of course the structure is similar to the enantiomer that we have demonstrated for this case. So that, that one, as I have said there, for the concept of chirality or chiral, for chiral compounds, these are compounds that have got a property that is whereby they cannot be superimposed upon their mirror image by a combination of either rotation, translation, or conformational changes to their structure. So therefore, we are going to just have a summary of what we've discussed, and then we wind up. So if this mirror image cannot be superimposed upon its, this just a structure cannot be superimposed upon its mirror image, there's a specific name that we give to this particular carbon that is located at this particular center of the tetrahedral structure. And this is normally illustrated using an asterisk, and that asterisk, of course, or just asterisk, which is normally a small x that is located at that point. So that one is used to indicate the chiral center, what we refer to as the chiral center, or the stereogenic center, or just specifically the stereo center, which of course is illustrated using the carbon in the asterisk at a specific point. So in this case, we're going to encounter different, why is this concept important? We're going to encounter different molecules, especially the ones that deals with the carbohydrates and proteins, which assume this kind of a structure. And these molecules are very essential, especially now that we have mentioned about the concept of proteins, which are basically the polymers of amino acids. So amino acids are the building blocks for proteins. So in this case, we're going to see that different molecules like these ones, which are very much essential for life, are going to appear or having a structure of this particular kind, which we're going to find that this is going to dictate their properties. So in an essence, the study of stereochemistry under the concept of enantiomers, under the concept of enantiomers and chirality, is going to give a basis for us on how to try to determine how molecules of this particular nature are going to behave going forward. So in this case, this concept, try to remember it as we deal with the concept of proteins and molecules, so that whenever we mention about the chiral centers or the stereogenic or the stereo center, that is going to appear in our mind, that this is what we are getting to that or referring to. So in that case, we're going to stop there for today, guys. So thank you for subscribing to our channel. I know that majority of us maybe are just trying to having a view, but it's good for us to subscribe so that in case we have a new development or trying to have a concept, we can be able to relate to or try to discuss together to improve. So for that case, that is it for today. Thank you. Bye. God bless you.